5 seconds ago, we talked about overview of Boolean logic and gates algebra standard forms. Today we're going to do circuit optimizations, and we're going to skip over part 3 because that's really covered inside of Verilog, and it'll make more sense if we just stick to Verilog. All right, so circuit optimization. Our goal is to basically minimize the circuit as much as possible so we consume the least amount of area, the least amount of power, and consume the least amount of time in order to accomplish our goals. The 3 metrics we're going to start with right now is literal cost, gate input cost, and gate not. This makes a lot of sense with the picture. When we get to the picture, here we go. Wow. So example 1, we have function A or B and C, or not B and not C. So just to help you out, A, B, or A, C, B, C, A actually is right here. We're nodding B and nodding C and goes into this AND. That represents this guy. B and C is representing right here. And then the AND, the outputs of those two, plus the AND go into a final OR, which goes into the F. So, question is, what are the literals? Well, those are the literal inputs to each gate of the that are coming from your initial values. Notice that they're not gate outputs. They're just your literals coming in. So you have, in this case, 5. And then your gates are the additional 2 gates that are presented right here. So that'll be 7. And so the gate cost right here is 7. Your literals is 5 because you have 5 literals coming in. Your gate cost is the extra 2 in between here. And we don't count that last one. And then your gate with knots is you basically double up on the knots and count the knots as something additionally. Sometimes we don't count the knots, and the reason for that is a knot consumes 1 gate delay, and sometimes you can come up with other tricks in order to optimize the knot away. So it's best to keep it separate. All right. So the top one, we have a literal cost of 6. That should be, from the picture it's obvious because you 1, 2, 3, 4, 5, 6 to the initial gates. Notice that this gate has inputs coming from other gates, so this only has 6. You can easily see that from the function, 1, 2, 3, 4, 5, 6. The total gate cost is 8 because there's another 2 outputs that go to another gate over here, so it's 6 plus 2. And the gate not is 11 because you do have 3 knots, namely the 3 knots coming here. All right. Are we doing well with example 2 so far? Because this is where things start getting a little tricky. So the literal cost here is 6. 1, 2, 3, 4, 5, 6. Even though if you look, well, no, we've got 1, 2, 3, 4, 5, 6 perfect coming into each of our diagrams, or each gate. Notice that this final one, the inputs are coming from the outputs of the previous gates. The gate input is 3 because you have that input over here. Namely, you can see that from the formula as coming in between each one. And then gate not is where you add the 3 extra knots right here to get to 12. This ends up being the same function, but the first circuit is definitely better because it consumes less area, and the gate and you can see that by the gate input cost as well as the fact that it's missing an OR. But that you can also tell from the gate cost that is simpler. So we would choose that one if we were trying to optimize a circuit. All right. Minimizing the gate cost of a set of Boolean reduces circuit cost, so we always choose gate input cost. In other words, the literals is a good start, but we really want to know the gate input cost because that's the total number or the maximum cost of the real circuit. So we always choose, we want to minimize gate input. We can use Boolean algebra or try and graph it out in a diagram to try and figure out what the answer is. That's slow and incredibly tedious. Also, how do you know when to stop reducing the cost? And do you ever know if you have the minimum cost? How do you know if you have the minimum cost? I mean, if you just saw us on the board, I got down to 6. I thought that was pretty good, but they had another one that went down to 3. So how do you know when you're actually at the minimum? So treat optimum or near optimum functions as 2-level, either as the sum of products or product of sums, and then we're going to introduce a graphical technique called a Karnaugh map, or I'm just going to call it a K-map, which will simplify our optimization techniques and can be used inside of a program. K-map is a collection of squares, and it represents the truth table. Let's go to a picture. Let's go to a picture. Here we go. Perfect. Whew. So a two-variable K-map. A K-map, by the way, its size is going to change dependent on the number of variables you have. We will start with the two-variable version. It will look like here where you're putting in your min terms. So we're doing a sum of min terms inside of this K-map. The first one is min term of 0. The one to the right will be min term of 1, and then the one bottom left will be min term of 2, afterwards min term of 3. Now, it's important to recognize how we represent this because it's not going to go 0, 1, 2, 3, etc., etc. So we need to figure out how this is coming about. Well, the first one, min term is 0, so that's where you start. And then it's adding 1 or only decomplementing the first variable. And then after that, it'll uncomplement the second, and then uncomplement both. All right, let's do a picture first. So let's see. Oh, here we go. You have your truth table over here with your 4 possible inputs. The K-map will give you the 4 possible inputs or another picture. In other words, your K-map is describing your truth table in a different format. ABCD, there's ABCD. That means that if you prove something with a K-map, since it maps directly to a truth table, you're also proving it for the function. Because the K-map is representing the truth table in a 2D graph. So for example, what's the K-map of just x? Well, x is, if x is 1, then it's obviously going to be 1. We don't care about y because we're ignoring it. Notice that this actually maps to x and not y, or x and y, because this guy right here is representing x and not y, and this one right here is representing x and y, because this is the min term of 3. See, min term of 3, so that one is 1 as well. Okay, how are we doing so far? Getting a little confused? Yeah. So the min term, how about of x or y? Well, if you, ooh, that is hard to read. Huh. Well, if you min term this out, remember we went from how we did that where we added, multiplied by 1 to get to the final value. Let me show you that on the board. Where are we? We have x or y. So that is equal to x or y, or y, x or not x, which is equal to x, y not, or x, y, or y, x, or what do we have here? Y, x not. Those are the same thing. There we are. Okay. So that's two variable. Two variable is kind of weird because it doesn't seem like it's giving you anything. 3 variable is where I think it makes a little more sense, although now the numbering system is different. So in a 3 variable K-map, there's different ways to represent it. The way we're going to do it in class is 2 rows and 4 columns. So min term of 0, a min term of 0, 1, notice that you have y and z up here. You have the first term is, 0, 0, 1. And then 3 is going to be 0, 1, 1, and then 0, 1, 0. Why is it written this way? Because every time you move from one cell to an adjacent cell, you are only flipping 1 bit. So from 0, 1 to 1, 1, you're just flipping the first bit, which is why it's a 3 and not a 2. And over here is a 2. All right, did they give you a better picture of this? This, I think, is a better picture right here. In other words, if you're looking here at this K-map, this bottom row represents X, the top row is not X. These four squares over here, these two columns are Y, these two over here are not Y, and then Z is the middle two, and then not Z is the outer two. That is how, an easier way when I look at it, to fill in what blocks need to go where. And if you were to actually set this down, because if you have, let's see, not X, Y, and Z, that means you have 0, 1, 1, which is 3. Down here you would have X, Y, and Z, which is all ones, which is why this is a 7. Well, this is a 6 because you're knotting the Z, which is the last value, so you have 4 plus 2, and then that's it, because you would have the 0. All right, you're giving me some blank looks, so let me show you. So, what's right here? Well, it's not X, not Y, and not Z. All right? So that's obviously min-term of 0, aka 0, 0, 0. All right? Here, not X, so 0. Not Y, right up there is 0. Z is on, so that's 1, so that makes it a min-term of 1. Right here, not X, 0, we have a Y, which is 1, and we have a Z, which is 1. So what is that? Midterm 3. Right here, X is still knotted, Y is on, but Z is knotted. So that is midterm of 2. All right, we're doing great. Perfect. Here, the X is on, the Y is off, and the Z is off. So that is midterm of 4. Sorry. 1, 0, 0, 4, 2, 1. So here, X is on, Y is off, Z is off. Oops. Let me rewrite that. X is on, Y is off, Z is on, so that is 5. Right here, X is on, Y is on, Z is on, midterm of 7. Yep. And then finally, X is on, Y is on, Z is off, so we have a midterm of. All right. Is that better? Okay. Hence why it's now 0, 1, 3, 2, 4, 5, 7, 6. It's the new math. Okay. So, why is this useful? Well, let's take a look at this. Let's say we have the sum of midterms 2, 3, 4, 5. We fill them in. And, okay, they're not going to show you why this is useful yet, but that's fine. Or you can get the midterms of 3, 4, 6, 7, and you can just fill in the map. It's helpful for doing this. You can learn the 8 locations. I never really do. I have to figure it out. Make sure you write them down. We're only going to do 3 and 4 variable K-maps. So I'm not going to try and make you go beyond that because that's just annoying. Okay, so we need to go to a picture. Picture, perfect. Here we go. Sum of midterms 2, 3, 6, 7. These are the ones, these are off. If you look over here, what's that function? Ignore everything underneath. Well, it's y, right? Because if y is 1, the answer is 1. If y is off, the answer is 0. So this is just describing the function f equals y. F of x comma y equals y. We could algebra it all out like this, or you can just see that y is, when y is on, you get a 1, When y is off, you have a bunch of zeros. So this is just describing the box of y. If you go down to 2 cell and y, okay, sure. This right here is describing, what is it, y and z, because that's what matters here. This one is describing not x and not y. Hey, we get animation after the fact. Ooh, and this one over here is describing, because you have not z and not x. Let's go to my picture, because that might make more sense. These 2 cells are y and z. These 2 cells are not x and not y. And then these 2 cells are not x and not z. Right there. Because if you look at which ones are occupied, you can look at which ones are occupying. In a 3 variable, you have to have 2. You have to occupy 2 cells if you have 2 variables. In the 4 cell, that on this side is going to be not y. This one right here is just z. Do we get another picture? And the ones on the edges are not z. Do y'all see how I'm getting this by just looking at it? In other words, what are these 4 right here? These 4 right here. Just not y, yeah. Right. How about this top row?
X.
Not x. Correct.
Yeah.
How about these 2 columns?
Not z.
Not z, right. And then, so let's go back to 2 square. So let's do these 2 columns. I think someone said x.
X and z.
X and z, all right, great. And then let's do these 2 columns. I mean, these 2 squares, sorry. These 2 squares.
Z, X, not z.
X and not z. And then, of course, the individual ones like this one, it's just not x, y, and not z. So, yeah, it's all 3 of them when it's 1. So notice that when you go from 1, when you go to 2, you're knocking off a variable, and then when you double and go to 4, you're knocking off a final variable. Yes?
All right, so I've patiently watched and listened to this, but what is this for? What is the purpose of this thing? Because
No, well, hold on one
I
moment.
have no idea.
No, we just did.
Well,
You take your circuit, you convert it to a sum of minterms, which can be automated inside of a computer.
Okay.
You create your K-map, which is a 2x8 matrix. You fill it in, and then you run a couple of tests, and you realize that in your K-map, the right half is all 1s, and the left half is all 0. Therefore, whatever circuit you just wrote, however complicated it is, has to be the function f of x comma y comma z equals y.
Okay.
That's why. You asked me why we're doing this, and this is why. Because since, now, what you may not be understanding is why does this work? And that was because the K-map maps to the truth table, and it maps to the truth table in the way that we encode it with the sum of minterms or the product of max terms. Well, in this case, we're doing the sum of minterms, and that's how we encoded the K-map, and then we were able to automate testing, at least in this situation. We haven't gotten to how we're going to go more in depth about it, but right now the simple test is, in this case, if the right half is all 1s and the left half is 0, it has to be y, no matter how complicated your circuit was.
Okay, sort of got that. I'm just going to leave it be for now. We take time to think about it.
So you basically just say it's another method of simplifying an equation. To
It's
see
an
the
yeah, it's an automatic way of optimizing a circuit, or simplifying it, or improving its performance. And improving by performance, we mean reducing the number of gates you have, or the literals.
Make more sense when we do something.
Yeah, it makes a lot more sense when we go to the example.
When I started doing the problems where it's
All right, so let's do this one. What's the answer?
Okay, so are you trying to see what that creates?
Mm-hmm.
So
Well, first off,
okay.
what's the biggest square we can make? Z. All right, so. All right, and we only have one extra box. So what's the biggest box we can use that covers that one? What?
2.
Yeah, 2 variables. It would be y, which is this column, but we don't want to include this one, so we need to also not x. So it'd be these 2 guys. There's our optimal circuit.
Yeah.
Because we've covered it, anything not included is a 0, and we just covered the ones. There's the z, and there's the not xy. All right, we're going to do this one more, and then we're going to run out of time.
Okay. Just trying to remember what
So we got x naught x, and then we're using, we're going to do it this way, y and y naught, and then we're going to have our z down here. All right, whoops, I forgot to write it down. So 0, 1, 2. Remember how that trick is, how it went? Yeah, it's just flipping the bit. So where's 4?
Bottom left.
Where's 6?
Bottom right.
Bottom right. Where's 7?
Bottom of that. Yeah. That one.
Oh, I wrote a 7.
Supercomputer.
All right.
Just blows up because there's no one to do with it.
All right, what's the biggest box we can make?
I think you can only make a 2. Wow.
4.
Wait, hold on. Oh yeah, you can do the corners.
Not Z.
Not Z. Yeah.
Aha, got you.
Got
Okay.
me.
I will go with green.
Ooh, yeah, multicolored shot. Breaking out colors.
So we now need to include these 2, include these guys without including the other ones. Hold on, we got a not x and not y, so not x, not y, that's this guy up here. Loud and proud.
XY.
XY. So x and y, that's these 4 right here. So there's the, well, from our interpretation, the optimal circuit for this. So no matter how crazy you wrote it in Verilog, it converted it to a sum of midterms, put it in here, did a quick analysis. This is the actual optimal circuit from whatever you wrote in Verilog. All right?
Just clarify. So, ideally, you want the one with the least amount of overlaps because there was an overlap in that one.
But you can't.
Yeah, but yeah, so you are correct. Technically, if you can eliminate all the overlap while using the largest term, it'll be optimal. In this case, I can tell you this is an optimal circuit because you don't have many other choices. You don't. We will get to next class about other choices that will impact it. But for this one, you don't have any, so you can pretty much guarantee that this was an optimal circuit because we're going to start talking about prime implicates. And that's what's going to actually tell you if your circuit is optimal or not. But I can tell you by looking at it that this one's optimal because of the way it's laid out. But when we go to prime implicates, it'll make more, because what you said is true. But we'll be clear about that next class. It's also a lot easier to see this when we go to 4 variable because we only have 8 squares. So there's only so much you can do with that. But when we go to 16, a lot of this will make a lot more sense, or get that W in there.
Yeah.
All right.
It's actually fun when you figure it out.
Any other questions about what I wrote up here? Here's my question to you. Which one looks easier? This or writing out the algebra? looks easier at this moment.
That's fine.
Yeah, right. That's why we're doing this. Because this one is a lot easier. It's also something you can, you can't fully automate it, but you can automate a lot of it to give you at least a more optimal circuit quickly.
It's just a lot of information at once, and my mind is kind of.
Right, I just threw a ton of terms at you. But that's why we have homework, so you'll remember it. The homework is going to go in order. Ooh, a speed delay.